everyone and welcome into yet another live stream. Today I have something special for you. That's because we're not doing a usual Make It stream. Oh no, we're going to do a Make It science stream in which actually will explain some science. And I say we because it's not just me. That's because right here with me is Remko. Oh, me? How am I doing? Oh, yes, we haven't spoken in such a long time, that is true. Well, my day is going well. How's your day going, Remko? Oh, has it now? Oh, that is good. That is really good. Remko is silent. Oh, no. Remko, are you silent? You are. Why are you silent? Don't worry, I'm going to fix it.
Silence is the key to humble your enemy.
It does look as if we're debating. I fixed it. There we go. So
there we go again.
everyone watching, how is your day going? How are you doing? I didn't see the microphone. Yeah, Pandashan, come on. You know how long it took us to set up this live stream? Unbelievable.
Ages. So is my microphone better? Can you guys hear me?
It is
in
working
chat?
right now. Yes, don't worry.
Perfect.
Well, everyone, I feel like there's no point in delaying it because, to be completely honest, yes, today's live stream is going to be a bit different. And that's because we're actually going to explain something, a coherent topic. We won't just ramble on like in a typical Make It live stream. We're actually tying a theme over the course of the live stream. And that will be, what will it be, Remko?
Well, today we will be talking a lot of physics. And we will also be talking a lot of equations from the physics. In particular, let me tell you guys a story about space and time. A story about forces and energies. A story so grand it withstood the test of time as centuries passed. This story I will tell you with cosmic awe and galactic respect. And perhaps along the way, we will find out that actions really have consequences. It's a physics live stream.
Wait, that was really elaborate. You took me by surprise. I had to get a drink myself.
So today we will be talking a lot of actual physics, bachelor physics, and I am assuming a couple of preliminaries, or we are assuming a couple of preliminaries, among which, for example, position, velocity, derivatives, and force. And we will also even see a tiny bit of integration, don't get scared. But if you have any problems with any of the material, any questions, unfamiliarities with concepts, just ask in chat. That's what we're here for, that's why we're streaming.
Yes, exactly. That would be a specific difference. We have planned this a fair bit at least, and we did realize that if we only wanted to focus on the let's just say more advanced physics for the sake of the live stream themselves, it would still be a fairly long time, so we might skip over some of the basics. If some of the basics aren't clear to you though, don't worry, because they are only basics relative to the actual topic of the video. You can still ask and we'll still be more than happy to explain. I might even have a visualization or two about them ready just in case someone asks, so you know. No harm, no foul, we're prepared. Hopefully.
Also, look who walked into chat right in time for a shout out.
Would you look at that? All matter? Is that all matter? All matter watching the live stream right now. All matter, who's famous for drawing certain things, certain characters, even at a table with two different coffee cups chatting together. That is all matter. Hi there, all matter. Oh, I do have to say, they are absolutely lovely, the avatars. They are phenomenal and they work exactly like they're supposed to. We did spend a significant amount of time chatting and just looking at ourselves talking, which we honestly spent a lot more time than I'm willing to admit doing that. But that's
I mean,
not important right now.
look how cool they are, though.
They are incredible. The hands are oddly close when we're both at the same time, but there's something you cannot really unsee. But yeah, seems like you're soft launching a podcast. Make it, Sebas. You will see this. This will be more than a podcast. but
This has more preparation than a podcast.
But you know what? Enough foreshadowing, because we foreshadowed enough. Let's get started. And what will be the first topic we're going to get started with?
The story is going to start with Newton, specifically Newtonian mechanics.
That's all the good ones.
The reason is purposely easy, so you guys hopefully stay. Let's briefly recall Newtonian physics as everyone knows it in high school. In particular, let us recite the Newtonian laws and postulates. So, we know there are 3 of them, or so we have been told.
Oh, so they tell us.
Or so they tell us. Well, I'm going to give you 3 of them. So the first one is a body remains at rest or in constant motion unless acted upon by a force. I'm briefly going to through this. I'm not going to stay long at these.
But yeah, the first one, quite simple enough. Newton is a genius, so Newton did figure out that when you don't move an object, it doesn't move. It's honestly, it's impressive.
Yes. So what this is actually saying us is that in order to describe particles, systems, planets, whatever we want to describe, we need the notion of a force. The dynamics of the physics are entirely determined by this interplay of the fundamental forces. And this law by itself is also the concept of inertia, that without forces, a body does not act. So we need forces. That is basically what this law is telling us. F. All right. Let's move on to the second law, because this one doesn't have that much to hide. Second law is a lot more interesting. And it tells us that the force on an object is equal to the acceleration times its mass. And this is Newton's famous law.
Yes. F equals to AM if you want to your all physicists to hate you.
Let's actually take a second to digest this. I see a lot of comments in chat, and yes, we are getting there, don't worry. But let's first of all write the acceleration as we know it as the second derivative of position. So this is the part where we need some content about derivatives. If there's any questions, ask in chat. And what we can do is write it a bit more explicit as a time derivative of the velocity. And what this means is if... Oops, I keep writing bigger and bigger. What this means, if we want to regroup, we have a quantity that we take the derivative of time to. And this quantity is what we're going to call momentum. So the second law of Newton basically tells us that the force equals to the change in momentum with respect to time.
Is everything clear so far to everyone watching? Is everything clicking together? Because this is effectively, we're starting at Newtonian mechanics. This is I know it's not advanced, but it's a very important foundation for us to start our journey. So, right, everything makes sense. On the very beginning, we have FMA, the classic, then A as a second order derivative, position in relation to time. So,
there is a hidden assumption here that the mass doesn't change with respect to time.
oh,
I mean,
your inner
if you're talking about
physicist.
rocket fuel, what gets consumed while you shooting up the rocket, then yes, this equation does not
You
hold.
don't.
But in usually we are.
You really don't get to say that honestly very often. But Remco, we're not doing rocket science today.
Unfortunately, no, but we will get there. Don't worry,
Tune in
guys.
next week. Okay, no, no. But yeah, obviously, if mass stays conserved. What's the difference between F is equal to MA, F is equal to... there is no actual difference, Sebas, because they're all equal. There are just different ways of noting down the same thing. Oh, unless, wait, no, you're asking FMA and this, and FPT... Oh no, and all of them. Yeah, no, they're all equal because they're all the same thing. Acceleration is second order derivative of position to time. If you take mass multiplied by velocity, you get momentum, so... that's why the momentum to time. All of these are just the same thing because all of them are equal on their own. Why is the second order derivative of position acceleration? Well, that's because that's how we just define it. The first
That is indeed definition.
that it is by definition the second derivative of acceleration. It's like the second derivative is acceleration. It's like first derivative is velocity. You know, that is kind of like asking. What's a bit of a tricky thing to come up with analogy before, but that's kind of like asking why is velocity position in relation to time. Well, the reason why velocity is position in relation to time, if you want to, you know, you could have position in relation to position if you're doing it in different directions, or time in relation to time if you're really having fun. But the reason why velocity is position in relation to time is because that just was the most useful, and that's how we by definition that is what it is. Because we say it is. Well, we invented the concept of acceleration and we just defined it as second order derivative of position in relation to time. Because that's what allows us to check how velocity is changing. And velocity is important because that's what allows us to check how position is changing. And without mind, third law.
Yes, third law. So the third law of Newton says that if two bodies exert forces on each other, these forces will have the same magnitude but in opposite direction. This is basically the law behind action equals minus reaction. We can investigate this a bit because this law has a very important property of systems. So, for example, if we consider two objects having a force, then we can look at the total force of these two objects, which is just the sum of the first one and with the second one, where this is the first force, this is the second force, and we know these to be equal but opposite. So if we don't really care about that much of vector analysis, we are just going to write it scalarly, and we will see that the total force is 0. That is what the third law is telling us. But what this implies is we just wrote down the force, and in this case, for the total force, we can do the same. We wrote it down as a derivative of momentum. So what we see is this force needs to be 0, which means that the derivative of the total momentum needs to be 0. So what we get here is momentum conservation. And this is also one of the reasons why we use momentum instead of velocity, even though they are similar of a notion. They both describe the direction and the
Mass rarely changes.
Yeah, the motion. So yes, the third law gives momentum conservation. Now
Dark is asking for the fourth law of motion.
Oh, that's a good one. No, I do not have a fourth one, but I do have a 0th one.
What we're doing with Galley's field, you know, finite fields. After 3, we go back to 0. That's...
I'm inspired by thermodynamics. There you go. I added the 0th law, so you can be happy, Dark. Bodies are made of particles, and this is usually the case. Let's not talk about dark matter and dark energy here. not yet. So what we have now is we have a formalism that, given a force, we can determine the dynamics of the system. Of like we can see how it moves, what its velocity is, what its acceleration is, just by doing some integration or manipulation with our variables. So the one thing that is missing here is the force. We need a notion of a force that helps us. That is our input for this formalism. Now, there's a lot of examples, such as we could consider gravity. We have all seen this equation. This is a force we could use, and then we could calculate the dynamics. We could consider electrodynamics. We could consider the normal force, the friction, anything we want to consider, basically. It's just, in order for this formalism, this Newtonian formalism to work, we need a notion of a force, and we need to apply the formalism. That's determines the entire system.
Yes. Okay. So far, I imagine everyone is clear on this. I feel like forces are something that's basic enough that is at least intuitive. Fairly enough.
I wrote down.
We don't appear to have any questions.
Yes, so I'm going to give two examples here. And the first example I'm going to give is the easiest example, namely that of the free particle, as it is called in physics. The free particle, it speaks for itself. It basically asks the question, what if there is no force acting on this particle? What if this particle is just so special it doesn't have force acting on it? Well, then we can immediately write down the force equals 0. What this means is the force equals to acceleration times the mass from Newton's formalism now needs to be 0. We can once again write this using the derivative to momentum. And since we know that this equals to 0, this means that taking the derivative of something and getting 0, that means that the momentum has to be constant. So what we get is, in this case, momentum is still equal to the mass times the velocity, but velocity here is constant, and the momentum is thus also constant. That's very important. It doesn't change over time.
Okay,
now
to accent this right now, real quick. F is equal to ma, everyone knows. It has to be 0 because that's just the example we're given, right? The free particle, that's the whole point of a free particle, is that there are no forces. F is equal to ma. But from the equations higher up, you can see that F is equal to ma is equal just to the derivative of momentum in relation to time. These two are equal. So that's why this right here could also said to be equal to the momentum. Or rather, more specifically, very importantly, the derivative of momentum in relation to time. So if the derivative of momentum in relation to time is 0, that doesn't mean that the momentum is 0, it means that momentum isn't changing. And as such, momentum is constant. Just to accent it, really put it out there. This effectively states that if there are no forces acting on it, that means the momentum is constant.
Yes, and this is indeed, once again, under the assumption that mass is constant, and I'm always going to ignore this. We're not particularly ignoring air resistance because I'm already saying it's free particle. It has no forces acting on it. So that includes air resistance.
Force. We're ignoring a lot more than air resistance in this case.
If you want a particle that is not being acted upon by forces, you would need this particle to be alone in a universe that doesn't have any
You would need
energy.
a different universe.
I don't think you can get a universe because the universe itself gives energy, and so the particle is not.
Yeah, it wouldn't be able to exist in our universe.
It's a thought experiment. We're going to stay with the thought. This is just all our imagination. Anyways, saying that the velocity is constant means that we can write. Once again, we know that the velocity is the derivative of x to t. So we can write that the position is linear. So it is the velocity times time plus some constants. We don't really. It doesn't really matter what the details here are. The whole idea is now that we have this expression, this is the solution of our system. So we probably need to give some boundary conditions, which means we need to say where a particle is at time. For example, time is 0. And if we do that, we have solved the entire system. Nothing is going to happen. Everything is deterministic. Is that clear?
Yeah.
Is there any
In this
questions?
case, we're already starting with one theme that's going to be, that's going to happen over the course of the live stream, which is that really often, in physics especially, you're going to have a single character represent different things that are all tied together. What do I mean by that? Well, something that most of you out there were probably already used to, and by probably I mean most definitely, is x describing position as in the value. So when you have a cube, you describe its position by x. The lower the value, the more to the left it is, the higher the value, the more to the right, something like that. In this case, this is a function x of t. The reason why it's a function is because position changes over time, right? It's the particle still has some momentum, so it's clearly traveling. That's something that I will point out, despite how to physicists it is obvious. I will point out over the course of the stream because I know that it can be confusing when you have certain things that are both sometimes used to denote variables, sometimes functions, and sometimes they might be even wearing a certain article of clothing. So this is just effectively how the cube is traveling. For each different time, you get a different position, or you could get a different position. And as such, you need to describe it with a function which has a unique input.
Yes.
I feel like
thank you for being the guard.
I was doing filler just to see if anyone has any questions, but no one has so far. So,
Darek, we're going to do that in the opposite way. Don't worry. So let me just, for this free particle, let me just quickly, for future reference, mention its kinetic energy. This kinetic energy is given by a half mv squared. And we can rewrite this a little bit by multiplying by 1 in a way that it is m divided by m, which is 1. And then, of course, we have everything else. And we can rewrite this as mv squared altogether divided by m. And we can notice that our mv here is p squared. I'm writing it in this form in particular because we will see it later. The main point you can take from this is that the v and the p are both constant for our free particle. So our kinetic energy is also constant. It doesn't change with time. It's just a single value for this particle. So that was the first example. Let's
that really
spice it up a bit.
Was the first example. It's tricky to come up with something simpler than the free particle.
Yeah, at this point, I would like, usually as a physicist perspective, I would say, let's give an animation, but this is so simple that it doesn't need an animation.
First of all, you. Oh, you. But second of all, the animation, effectively, this would be just a particle moving forward. And its kinetic energy graph would look like this. If we have a line that represents 0 right here, this would be the kinetic energy. This would be the potential energy. And so the total energy would just be the line overlapping. I know that the lines are crooked, but they all should be flat. Unless you have something else in the background, you would not be able to tell that a free particle is not just a static particle.
Let's move
and
to...
I wouldn't make that clear. This was not for the sake of clearing up. This was just... Shut up, Remko.
So let's move to a more to a second example that's more involved, that actually introduces some new topics. So let's first of all consider a linear force, and in this case I'm going to introduce the minus sign for a reason. This is the force when we, for example, consider a pendulum. So we have a fixed point. This is a fixed point. There is a string attached that is rigid, and we have a small ball at the end. This is going to swing like this and then back. The point of this minus sign is in equilibrium. If it's not moving, it's hanging straight down by gravity. Then if it's slightly to the left, the force, if this is our x-axis, this is going to be negative x, because this is 0x. So the force here is negative, which means, or the x is negative, which means the force is positive, which means the force is pointing that way. If we throw it the other way around, force is over here, x is positive, which means the force is negative. The force always wants to go back to this equilibrium point. And that creates this whole swinging of the pendulum. There is an assumption here. If you know the assumption, throw it in chat. I'm going to leave it for later because it's think about it. It will come back. Yes, of course there is no air resistance. That one doesn't count. So let's just use Newton's laws on this. We know once again F is.
Ooh, I think QWERTY might be close. I know we're
Yeah, QWERTY knows. Then you already know what the X is representing. So Newtonian formalism F equals m times a. A was the second derivative of position to time, and we now set this equal to our force. So this is a differential equation where we want to take the derivative of a function twice, and we will want to get the same function, but with a minus sign. So we need to take the derivative twice and get a minus sign. This is done by, for example, a sine or a cosine. We know that if we take the derivative of a sine once, it will give a cosine. If we then take the derivative of a cosine or the second derivative of the sine, it will give minus a sine. So the sine is a function we're looking for. I'm going to write down the general solution to this, which is given by the position as function of time is a times sine times k divided by m t plus phi. And let me introduce some of the symbols here. So the A is the amplitude. It basically tells us how far the pendulum is going wide. For larger A's, it will make a larger swing. For our phi determines when to start, when this equation is valid. Like, for example, we could start the pendulum at 0 seconds, but we could also wait a second and then throw it. And that would also be valid. And this phi fixes that. That phi makes sure we have the right solution. This factor here, the square root of k over m. I got distracted by Theo, my bad. This factor here, the square root k over m, is the frequency. We commonly write with the omega or w, if you will. This tells us how fast it is swinging around its equilibrium point. So once again, we have solved the system. It took a bit of effort this time because we had to solve a differential equation. In general, these two examples are the simplest examples. So any other system, you will find differential equations that are difficult or even impossible to solve analytically. You will need to find numerical solutions. But in this case, we did it. Good on us.
Wow, impressive. And we could even see what the energy of a system like this, because in the previous example, the energy of a system was unbearingly boring. It's just a constant line. But in this case, it is actually different. And the reason why is because this has not only kinetic energy, but it has a potential. In this case, there's a force acting on it. You gasped as if you were about to say something.
Yes, I should maybe show the pendulum.
That was.
I think this is maybe a good time.
That's why you gasped, because that's what I was building up to. Don't worry, that was the point. So, let's say that we have our pendulum, and let's say that it actually exists. What do the kinetic energy of that kind of pendulum actually looks like over time as it's oscillating? Well, first it's going to swing to the right, then it's going to very slowly swing to the left. In this case, since this is, can I already explain the QWERTY? What you foreshadowed with QWERTY getting it right, the assumption, small angles.
Yeah, sure, go for it.
Yeah, basically this is sort of small angles approximation, which is why it's actually oscillating this slowly. A fun little tidbit from behind the scenes: you have no idea how difficult it was to make an accurate pendulum with larger angles until we realized that larger angles aren't actually quiet. But as the animation goes on, you can see that the pendulum is oscillating and the kinetic and potential energies are oscillating as well. Why is that? Well, that's because when the pendulum swings to the left, once it reaches the extreme point, it stops. So it loses all of its kinetic energy. When there's no movement, there's no kinetic energy, and that's why the kinetic energy right here goes to zero. There is nothing. However, the total energy, which is the blue line, stays conserved. It has to stay conserved. That's one of the big rules, I would say, of physics, at least top 5, at the very least. And so where does this energy go? Well, that energy goes to the potential energy, denoted by this purple line. This right here, potential energy, is maximum when the pendulum swings further south, and then, once it completes a full swing, it will start converting that potential back into kinetic, like so. And then it reaches the middle point. At the middle point, it's traveling the quickest, which is why the kinetic energy is at its maximum. There is no potential energy, but then as it starts climbing back, it once again converts them. And like this, it goes on forever, effectively. No air resistance, once again, no any resistance, so it will just, the blue line will just stay flat and it will keep oscillating till the end of days.
Exactly,
Oscillator.
that's so poetic.
Oscillator. I can see you were busy in the background as well.
Yes, let's just write this down in equation so we can support our lovely animation. Once again, when we want to write the kinetic energy, it will be of the form a half mv squared. Now we need to do some effort to find our v, taking the derivative of x with respect to t. This is just simple differentiation. I already wrote it down. And this means that we found our kinetic energy, and it will be squaring this velocity, so it will be of this form. Now, as Megan mentioned, this kinetic energy is not constant. And this is because we need to take into consideration a potential energy here. In this case, it comes from the gravitational force. Specifically, if we want to write it down as an equation, it looks like this. The derivative of the potential energy with respect to x in this time, so with respect to the position where the pendulum is at, is equal to minus the force. Or in this case, it's quite subtle. It's not trivial where this equation is coming from. And I have some good news because we are going to derive this equation later. So first of all, we can simply by integrating, or I will give you another method in a second, we know that the force equals minus kx. So this means that the potential energy will be a half kx. Kx squared. And we can also see this because if we take the derivative to x here, we will just be left with x times k, which is exactly what we want. And then when we add kinetic and potential energy, we can use that the sine squared plus cosine squared equals 1. And so our total energy does not depend on time. This example is probably the most important example in all of physics. It is the infamous harmonic oscillator.
One and only.
And let's just say that no matter which field of physics you go to, you will always find a harmonic oscillator as the starting point. Everything will be described by harmonic oscillator. So, if I may so give some advice from a physicist perspective, know this harmonic oscillator, know it well, and you can basically solve almost every system just by approximation. There are more systems that are described by harmonic oscillators. We saw the pendulum for the low angle approximation. It also holds, for example, for a spring system with Hooke's law, which is the same law, which is the same force, and a ball rolling down a hill, as long as it's a quadratic hill, is also a harmonic oscillator.
Whenever you have a system that can be in any way approximated by waves, you will use a harmonic oscillator. And what's even better is that I've yet to see a system that cannot be approximated by waves. Sometimes poorly, but it always can. In this case, it would really be helpful if I finished the waves video before this, but oh well, foreshadowing.
Don't worry about it. We will get there. Let's quickly go back to the free particle, because we only talked about kinetic energy, and now we know a formula. Despite it falling out of the air by virtue of me, don't worry, it will be fixed. But we now know an expression to find the potential energy. Is there a lot of background noise from me, by the way?
Not a lot. It's subtle. Don't worry.
Good. This means that since our force equals 0, our potential energy needs to be a constant. Now, the lovely thing about energy, well, this needs to be a constant because once we take a derivative, it needs to vanish. That's why it's a constant. The lovely thing about energy is that it is relative. So what we could do is set this constant to 0. It's basically the same as voltage. You need a reference point, and in this case, we are making the reference point being 0. So there is no potential energy we need to deal with. That's also another reason why it's called the free particle.
It's as free as it can get. It doesn't change in any way across time. It doesn't change in any meaningful way across time.
Do we still have animations, or was this all the animations? I forgot.
We do not have an animation for a free particle. No, we do not. It was too complicated. It turned out to be too difficult. We
needed to solve the Einstein field equations for that.
Yeah, we spent a lot of time. We tried. We failed. The free particle was beating us. It was too much to bear. So far, this is what we've been over. Is everyone clear on everything? Because this is the background section of the blackboard, basically.
Yeah, we are going to start now for real.
Yeah, this was just a warm-up. 41 minutes of a warm-up, exactly.
I see no questions in chat.
I don't see any questions either. Let me just switch to live.
Let me take a small sip and we will continue.
Yeah, small sip is required. This is not something that can be done sober. Okay.
Hey, I was just drinking water with some ethanol.
I meant thirsty. I said... What did you hear?
Sober. You said sober.
I said thirsty. Let's carry on. We have the next...
So... we are now getting to the point in the stream where we get difficult words. And from now on, we're going to talk about Lagrangian mechanics as opposed to Newtonian mechanics. So what we saw as a quick recap, what we saw in Newtonian mechanics, we need a force, and using this force, we can calculate all the dynamics using Newton's law. So we need two pieces of information, two equations, and with these two equations, the entire dynamics of the system is determined. So the question we want to ask here is, can we do the same, but without the notion of a force? Can we describe a system without even thinking about the force? whichever force it is. And it turns out that we can, because we already have two pieces of information that can help us formulate this. And these two pieces of information are kinetic and potential energy. There is not a trivial way of combining them, but we can think of some things. First of all, we want to stay in. Well, we want to still be describing something of energy because we know what we want to. We know what we can do with energy. There's a lot of things in the formalisms that we can do with energy that we cannot do with other things. So first, let's try adding them. And in this case, what we saw is adding them gives us the total energy, at least for our systems considered. And this actually gives way to a formalism called the Hamiltonian formalism. This one is very potent in quantum mechanics, and we will be seeing this around later. But it is not that relevant in classical mechanics and not even quantum field theory, where we're eventually heading to. But as a humble foreshadowing of the future, this Hamiltonian in quantum mechanics will be a matrix with eigenvalues that are exactly, precisely the allowed state of a quantum system. That's enough foreshadowing. I'm going back to classical mechanics. So there's also one more thing why this is not that relevant, because the total energy, as we saw for both the free particle and the harmonic oscillator, are both constant. So in the Hamiltonian formalism, there is not a clear way to distinguish a free particle and a harmonic oscillator, even though we saw that they are vastly different. So let's instead look at the difference. Let's take the kinetic energy and subtract it with the potential energy. And this will give way to the Lagrangian formalism. This L is called the Lagrangian. It is a function of coordinates because we saw that the kinetic energy depends on V, the potential energy depends on X. So this is L is going to be a function of X and V, and sometimes we also have a time dependence, although we will not be seeing that well, definitely not today. In fact, I don't think I've ever seen a system with explicit time dependence. That's how rare it is. So this Lagrangian, it represents some sort of battle between the potential and the kinetic energy. It's sort of a tug of war. It tells us how strong the kinetic energy is with respect to the potential energy, etc. So we are going to investigate in this formalism. And this is what the rest of the entire stream is going to be about.
Exactly. Now, before we go on, is this clear at least? Because everyone, a good way to check if you understand this so far is to ask yourself a question if you understand why Lagrangian is a function of x and v. If you understand why it's a function of x and v, that's a pretty good sign that you have a fairly decent understanding. If not, then feel free to let us know. It is a live stream after all. And I don't see any questions. Everyone understands perfectly. We must be great at explaining things, Remko.
I think that is the reason.
Oh no, Punisher just said I never understood one thing. Well, never mind.
Oh, might switch back to top chat. I see. That's why I'm missing messages.
Okay. Well, in that case, I suppose carry on then.
As an answer to Qwerty's message, why is there a standard model Lagrangian and not Hamiltonian? Precisely for the reason I just mentioned. The Hamiltonian doesn't give the right structure, it doesn't give the right information. Actually, that's not entirely true. It does give the same information as the Lagrangian, but the way of using the Hamiltonian, the tools that you manipulate the Hamiltonian with are different from the tools you manipulate the Lagrangian with. And in quantum field theory, the Lagrangian is straightforward. because you can write it as the action, which is everything you need. This is a foreshadowing of the future. Whereas for the Hamiltonian, you can't really do this without reverting back to the Lagrangian, and that's why there is no standard model
Okay.
Hamiltonian.
Also, Pandashan just asked an absolutely phenomenal question. But I don't know how much of a rabbit hole can we go on this. If L is a function of v, doesn't that mean it's a function of x? Because v is equal to dx dt. And instantly,
That is an
in my head,
excellent question.
in my head,
we are going to get there right now. Yeah.
there's a really question in my head. I instantly just got hit with the Fourier transform, just slap across the face.
Oh, we don't even need that. It gets better.
I know we don't, but for obvious reasons. Pandashan, you will see in a second.
Right now, because
Literal second.
Because there is one caveat which makes the entire Lagrangian formalism so difficult and abstract for newcomers. And this is the concept of generalized generalized coordinates. And let's, instead of explaining this concept, because it is so unintuitive, let's just straight go for an example. Let's go back to our pendulum. We have a little pendulum with a rigid string with a bow at the end and equilibrium position. What we can do is we can describe this in terms of its displacement in x and y. So maybe there is actually a nice visualization for this, if I may so humbly request the animation god.
The animation god is pleased with your sacrifice.
Yes, exactly what I was going for. So for the pendulum, we can write this in terms of the x and the y. And also we know the derivatives of the x and the y. So in total, we have 4 different values: the x, the y, the derivative of x, and the derivative of y. However, we can also just consider something else. In particular, we could consider the angle of the rigid, of the pendulum. There is also a nice visualization for this one. And now, because our string has a set length, so our r in the polar coordinate description, our radius is constant. This theta, this angle, is sufficient for describing where the pendulum mass is. So what this means is, instead of using x and y with their respective derivatives, we could also just use theta and its derivative. This is, instead of 4 variables, we have now 2 variables. And the whole concept of generalized coordinates is that we want a minimum number of independent coordinates together with their velocities. And so in this case, we would, if we want to describe a Lagrangian of our system for the pendulum, we cannot write it in terms of x and y. We have to write it in terms of the angle, because that is our generalized coordinates. It doesn't work without generalized coordinates. There is also a side remark as an answer to your question. If we want to use the Lagrangian formalism, we will have to describe the position, in this case the angle, together with its velocity as independent. So they are not the same anymore. They are not related, even though, yes, they are related to a derivative, but the action of a derivative is an independent.
You can think of it as like the position. It's kind of a loose analogy, but like you can think of it as a position changing in the future. So if you have a ball, if you throw it, you can measure its position, you can measure its velocity, but its velocity right now in the instant isn't dependent on the position, nor is its position dependent on the velocity. Its position would change according to velocity, but like right now, you can have any position with any velocity you want. It's kind of a loose one, but it's the best I can come up with.
Yes. They are both functions of time ultimately. So in that sense, they are independent. They only explicitly depend on time, or implicitly.
I'm starting to get it now.
Um,
Thanks a lot.
Let me also give some general notation, because you will find a lot in the literature that for generalized coordinates, they are using the symbol x, where x is just any coordinate. So it could either be x, so our position, or it could also be theta, an angle, or it could be any notion of, well, of coordinate that you can think of. And for its time derivative, which we usually write as dt, dx dt, the usual notation is just x with a dot, where the dot always represents derivative to time. This, if you do this in your equations, you actually start to look like you're actually doing very cool physics. But for this stream, I will still be writing the x, the v, and the momentum, everything for the sake of clarity. But in literature, they will always adhere to this notation. And for cool reasons too, because I really like putting dots on my variables.
There is something else you can put on them, but wow, a second foreshadowing it did.
Not the foreshadowing.
Not the foreshadowing again.
So, can we see the pendulum again?
Obviously. Absolutely. Okay, there we go.
Yes, just appreciate it for a second while I take another sip. A lot of time went into this one, even though it looks so simple.
No, into this one it didn't. It was the other one. It was the energy one.
Yeah, okay, but we learned from that one.
And yeah, in case,
So,
once again, just to go over it real quickly, basically the intuitive way, let's just say, to describe it would be with two position variables, but the whole point here is that two position variables are unnecessary when you can just do it with one, since one is equivalent to describing it with two. You're always trying to get the fewest number of coordinates. Okay, no questions. How about we do it with three? How about we don't?
I was going to do no, I was doing a fun section. Let's go back to the drawing board if we can. I would be very pleased. So we have x. As a little foreshadowing for the next section. Don't look at that. You did not see that. We have the position. So our velocity would be x dot. This is v. Our acceleration would be x dot dot, which is also equal to v dot, because it's the derivative of v with respect to time. Now, if we want to take the derivative of acceleration, I find that there is no recognized symbol for that. And that's why I need your help, because I really like this symbol. So if you guys start using it from now on, just put three dots like this and not like this.
Yeah, everyone needs to start doing physics with jerk. We need to introduce jerk to physics, just so that.
Stack. Yeah. This is the jerk indeed. But start stacking the dots. Don't put them next to each other, stack them. This looks way cooler than the other one. Imagine the next one, which will just be x dot 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 dot. Look at this. This looks like dominoes. That looks way better than putting them side to side.
Also,
So that's just a little, yeah.
Also, speaking of the three variables, which I said we shouldn't do, Pantashan said we can do it with zero variables, really, because theta is approximately zero, so the movement is negligible. You know, it's a small angle, so.
You know what? I don't like that. We don't have a pendulum anymore.
Imagine the hovering ball.
Why?
Free particle.
This is. There you go. This is.
I love
better.
the notation there, by the way, in between the dots you used.
Yeah, I mean isomorphic. They are the same, up to something, up to Theo. Anyways,
Isomorphic up.
next section. The action. So
The
let's go
conflict.
back to our Lagrangian. This is where stuff gets real. This is where we see that actions do have consequences. The Lagrangian as difference of kinetic and potential energy. Once again, it represents some sort of battle between the two. What are we going to do with this? How are we going to make this useful? Well, let's just look at a little graph where we plot the potential energy versus the kinetic energy. And let's say we have a system. So we could have a pendulum, we could have a free particle. In this case, not a free particle, because then our potential would be zero. Let's just say we have some system. Say a rocket, whatever you want. So we are doing rocket science. Then this system has a certain potential energy. It has a certain kinetic energy. Now, let's just say we have another system here. Or rather, we want our original system to go to this system right here with a different potential energy and a different kinetic energy. Then, well, we have our first problem already. How are we going from this one, from the first one, number A, to number B, system number B? We could just work with a straight line. That's valid. But we could also go like this. We could also take a loop-to-loop or a couple and end up here. Or maybe for a final one, we just go around the A once again. What we have now created is a path in the phase space. This kinetic and potential energy is called the phase space, or at least when you write them back into position and velocity, they are really equivalent in a way. So perhaps instead of considering one path, we should maybe consider all of them as a cool superposition and sum over all of them. Wait, 1 second, I'm getting a call.
Don't worry.
Yes. Remko speaking. All right. Someone is saying something to me. Wait, what did you say? This is the path integral of quantum field theory? And we're still in quantum mechanics? And I'm not allowed to go this fast without having to talk about quantization? Well, my bad. Sorry for that. We are not talking about summing all of these paths. There is physics police apparently. They are angry. So we need to pick out one single path. And the question is then, which one? Well, as a physicist, yeah, go on, make it.
No, I was gonna say we can ask everyone watching to see how many people are actually paying attention.
Yeah, pick a path, guys.
If you had to bet your life, bet your entire life everyone around you, or on which path to pick in between A and B, which one is it? You have to pick now. Ash
Yeah,
said, pick the longest possible path.
You know what? That is possible.
It never reaches B.
You know what? From a physics perspective, from an advantage point, I will just give you guys the answer. We need a quantity that tells us which path is the best. So we need a quantity that gives us a rating to each path. And this quantity, I am just going to humbly write down as S equals the integral of the starting time, which means we are sitting in A, we start a time, we let it flow to B, and then we end the time. So we let it flow from the starting time. Oh, you don't like my integral?
It looked just like your S. It looked like S is equal
Okay,
to S.
okay, fair. I will just make it the S proper. And then we integrate over our Lagrangian. So this is our integrand. which depends on x, v, and also time, but not really because we don't care about time. And ta-da! We now have a quantity. Well, you have to trust me that it works, but we now have a quantity that tells us which path is best. In particular, let me explain this a bit because this is probably very vague. So, first of all, this integral gives us a number. So, the action is going to be just a number, a real number. What we do, there is a little algorithm to work with this. What we do is we start in number A, and we pick well, in this case, number B. We perform this integral, we get like a score. We then pick another point, so for example, point C, we perform the same integral, starting in A. We get another score. And what we get is sort of a landscape with potential, again, times kinetic energy. And we get, starting from this point, we get sort of a landscape. And perhaps we do have some sort of visualization for this.
A landscape
because that would make it
roughly like this. Like a heat map.
Like a mountain height map. Yes, exactly. It will look something like this. And so realize that each of these points have a particular value, a value of the action. And in some sense, we are looking for an optimal way between kinetic and potential energy. That is what the action does, because it tells us how kinetic energy changes with respect to potential energy when we move along some path. So each of these points has a certain value, real number, and perhaps just so simply we could plot this in a way that is, for example, 3D.
So something basically like this. Whoa.
Whoa, we have an animation. Someone did their job.
Someone spent a lot of time on it. But then between point A and B, for example, we would basically have a line that goes like this. And the crucial thing is that it has to like basically follow the... It has to basically follow the environment on which it is. And if we look at it from the side, you can see that for sometimes that means going up, then going down, then going up again. Sometimes it means just going down, maybe like this. And sometimes, very rarely, it could maybe, possibly, hopefully, mean just being still. But this is basically our environment. Like so. Also, Timon says that he's lost.
You have Google, find your way. Google Maps.
You guys remind me about some very good notation. It's an intro channel on Discord regarding that notation. Also, QWERTY said it does not have to be with respect to time.
What do you want to integrate it with respect to then? Unless you want, I suppose usually you can take, at least in the case of light, you can take a parameter that sort of represents time. For example, proper time, or, well, not proper time in the case of light, but how is it called again? I forgot the name, but there is a parameter that is not time, but it's a translation that takes from time to something else, and you could also integrate with respect to that.
Also, back to the environment, I suppose. These lines, one thing which I only realized should also mention, these lines don't have to be straight, as mentioned. Basically, any path we want. So, for example, our path doesn't have to look like this, it could look like this. It could be confusing, it could be windy, it could just be absolutely all over the place. We can screw it up even more, we can add in just even a loop-de-loop, because why not? Who's gonna stop us? And then this is what it would effectively look like. It would be just very windy, confusing, and but still going from some kind of point A to some kind of point B.
So if you want the optimal path from going from point A to point B, you will have to take a path that doesn't increase too much in energy. So you will need a path that more goes down more than it goes up. The reason for this is something we will see very shortly. But Timon, you asked a question. The reason is that we're not integrating over everything, we're integrating over paths. So the action is literally just a path in, like, what Make It is showing right now. It's a path in this phase space, in this energy plot, which has some sort of value at everywhere it comes to. And yes, the quantum tunneling is allowed, but not in this classical system.
Oh yeah, we're still doing classical mechanics, by the way. I feel like I should mention this. Because it just now hit me that it might look... No, this is still classical.
Yes, everything is classical.
We haven't quantized a single thing.
So, yes, so far it might seem a bit vague. It might seem a bit arbitrary why they want to introduce this notion of action. And this is basically where the real magic of physics starts. So let's go back to the whiteboard. Let's create a section here because I had one section too little. That's a fairly straight line.
On the stream it looks straight, because I'm hiding that one segment.
Anyways, so in physics, there is a really, really important postulate. A postulate on the same level of Newton's postulates or law. It is that the actual physics of a system happens in the extremal values of the action, which in other words means that if we have a system, for example, system A, we give it some time to get into equilibrium, then we will find the system in either a maximum, minimum, or a saddle point, where a saddle point is basically both a maximum and a minimum. And surely there is no way to visualize this, right? This is we will all have to imagine.
It's like getting pretty heavy with the surely no way.
Like, we have had so many visualizations, so many good visualizations.
Really, yeah, we could have got so much more. But I feel like in this case, we should also accent the fact that I don't think we accented properly enough, which is that the optimal path means going down. It always wants to go down. That will always be optimal. It will choose to go down, or rather, it wants to go up the least. So if we imagine some kind of starting point, let's just say right here, because why not? Right here on this nice slope. Let me first ask a question. If we start with a point in this space, on this slope, what is going to happen to that point? Where will it go? Also, hello alpaca, hi there. You've joined at a very fortunate time, because normally on this live stream I'm not greeting people because I'm in the middle of explanations, but you joined in right as I asked the question. Very lucky for you. It would jump into my mode. Okay, you are brilliant answers. This was a genuine question checking understanding. Brilliant answers so far. Well,
You guys are really paying attention, I'm glad.
well, the answer is this point, which is very slowly, very, very slowly.
Yeah, let's just all imagine the ball is moving. Oh, look at that.
Why is it not moving? Is it moving?
So there's different starting points we could choose.
Unbelievable. It is broken. No, not this. Not now. Don't worry. I can fix this.
So while our expert is working on this, let me get you through. This is the
No,
details of the
Remko,
code.
Remko, this is why we did backups. Don't worry. Okay. There we have it, back to the environment, lovely. And so now, if we take the ball and if we put it on a slope like this, what's going to happen to it is... Oh, whoops, just to keep it as simple as possible, because right now the function itself is changing, which is not something we want. And then if we put on a slope, what we get is the point rolling down. And rolling down and rolling down until it finds, in this case, a saddle point. Yeah, this is a saddle point that it rests on in this case. If we want to, we can take this point, we can move it somewhere else, we can see what happens, like right here, for example. Well, if I had to make a guess, I would imagine it would go down to the local minima, and down to the local minima it goes. As you can see, it keeps going. But even better, on this side, we can see a graph of the energy right here. This line right here is the graph of the energy of the point. And you can see that it always wants to go down. And here's how much it's going down. Starting flat, then going over gradient, and effectively, eventually we'll just find the rest point where we'll just rest, like so.
I would like to reiterate here that the ball is not a ball in a classical sense. It is
this
system.
Yeah, this isn't a physical space. Like, this isn't X and Y. That's not it. It's an abstract space.
So, yes, what we saw and, well, what we simulated is that if we put a system in a landscape, give it some time, it will find a minimum or a maximum.
Or a saddle point.
Or a saddle point. It will roll down until it has nowhere to roll. This is called the principle of stationary action. Note that this is still an assumption we're making. It's more of an axiom that we're making, and in this case, it's an axiom underlying everything of physics. So, from quantum mechanics to quantum field theory to particle physics to anything. And well, let's just see what happens. Because surely, if everyone is taking this as an axiom, it will surely reach some useful results, right? Well, the first thing we know is it's an extremal value. It's a maximum, minimum, or saddle point, as I have said a couple times. What do we know about extremal values of a function? Well, we know that the function's derivative has to be zero at these points. And this is something that we can actually calculate. Now, it's not visual, it's a bit of math, so I'm just going to show it for those interested and also for the video's sake. You don't have to understand this. What is important is the final result. So let's start.
Also,
in the top
meantime,
corner.
Timon's asking, why is the phase space so funky? Shouldn't the value just increase as the absolute value increases? Because we're plotting potential energy and kinetic energy.
No, we're plotting an arbitrary system. We don't know anything about the system, so this is also an arbitrary phase space. We've plotted a random one. It could be anything.
In our case, we have literally plotted a random one. There's another function we can use that we also have prepared specifically.
You know what? Why not? Should we? Or should we do it later?
You know what? First you can derive, then we can have the fun.
Yes, okay, fine. I'll get it's a little cliffhanger. It's fun. It's a fun function. So, with the first thing, let me actually just write the action first. So, in case we forgot it, I'm going to use a bit of abstract notation. It's the integral of the Lagrangian with respect to time. What we are going to do now is we are going to make a change in a path. This is because this is a path integral. It represents a path in this phase space. So instead of having to deal with a normal function, you have to deal with x. We now have to deal with paths, and this is slightly different, but it's not that intuitively impossible to understand. What we are doing is when we have a path from point A well, in this case, we should probably give it small a and small b, and we want it to go from b. Let's just say we have a path. This is our x of t. This is a path that takes place in this phase space. What we now want to do is we want to vary it a little bit. Like what we usually do with integral is we have a point, we go slightly away from the point and see how it changes, how the function changes with respect to that point. We are now doing the same, but with a path. So what we're doing is we're slightly going away from this function. So it doesn't have to have the same shape. It is just the path needs to be close to it, significantly close. So you get all these kind of sort of paths. And let's just say I don't specify which path I'm using. I'm just specify that I am using one of these. I should probably mark the main path. This red one. This is our original path. We are going to use one of these white paths, and I indicate this by it is the normal path, but we add a little bit, and this could either be positive or negative. Doesn't matter. The main important thing here is that at the endpoints, the paths are the same, which means that the variation, as it is called, the deviation from the path, at the endpoints, it's going to be 0. That holds for both endpoints. Now we can actually see how our action is going to change when we take one of these other paths instead of the normal one. So this is we are dealing with the Lagrangian, which is a function of in this case, for simplicity, let's just entirely forget about time, as I've been doing all this time, but I'm also not going to write it down this time. Ha, pun. It's a function of x and v. I see I've already fallen into the habit of writing it x dot. It's a function of x and v, which means we are changing the path. We are also implicitly changing the... Well, we don't even care what happens with the v. We just know it's a function that depends on these x and these v. So if we want to see its change, we will need to see how it changes with respect to x. And this is indicated as such. And we will need to see how it changes with respect to v, which is written as this. And we all want this to be 0 because that's what it means to be in an extremal value. That's what it means to be in a minimum or a maximum. So what we can now do is we can rewrite this a bit. Specifically, we can write the second part of it, where the variation of the velocity, variation of v, we can just write this as the time derivative of the variation of x. We are assuming that variation commutes with the time derivative. This is a fair assumption for those who know what that means. Then, I'm missing my measures. Still integrating with respect to t. Then we are now going to use integration by parts, which means that we can write... This is probably the step where I'm going to lose half of the people. You'll see this when you're doing integration. It's one of the things of calculus. But effectively what you're doing is you are changing the derivative on this variation. You're putting it instead on the term before it, so the derivative of the Lagrangian with respect to the velocity, and you still got this one, and you can do this at the cost of your boundary conditions, so you will need to compensate for these. And what we know is, so this term needs to be evaluated at a and b, but what we know is that the variation at the endpoint they are they're glued to the point. So this entire term will be 0. So we don't have to worry about this. Very convenient. What we can then do is write one more step, and then we're done. So we're almost there. Which just factors everything. Oh wait, you go away. So writing you twice. One more step, which just factorizes, because we now got this one and this one. We can just take that out of the brackets. And what we end up with is this. Now comes the main crux of the problem, which is I have not specified which variation. So it could be any variation. So this expression needs to be 0, because that's what it means to be an extrema value. It needs to be 0 for every single variation. Now, if you have an integral that needs to hold for every single value, then this needs to be 0. Inside the integral, the integrand needs to be 0. And this is the result we were after. Namely, that the derivative of the Lagrangian with respect to x minus the time derivative of the Lagrangian with respect to the velocity, this needs to be 0. This is the very famous Euler-Lagrange equation.
You did. Oh, you did it. Oh, so I went for a lunch break, mate. I don't know what you're. You were kind of talking and such. I just went on to have a bite, you know. Went out, had a lovely evening. Anyway, as you were explaining, there's been a lot of confusion brewing in chat from time and again. What is the phase space? What are the axes and the heights? And I feel like I get the confusion. So basically what Timon is saying is that if you have a plot of kinetic energy to potential energy, then the Lagrangian would always be the same, because it would effectively be kind of like having a space of, hold on, if we go back to it, it would be effectively kind of like having, I think it goes from the way you noted it down, because then effectively you mean kind of like having a space of, you know, x and y, and then having a function that's equal to x minus y. Like in this case, this function would always be the same. In the same way as if you have kinetic energy and potential energy, then Lagrangian for this would always be the same. But we are not graphing kinetic and potential energy, are we?
You're also not graphing the Lagrangian.
Yup.
We're graphing the action, which is a single number that we get from integrating from one point to another in our system, in our phase space.
It is.
Yes. So we're just kind of what we're doing is we're just checking a path and giving a value to that path. So if we want to go from one point to another, we give the other point that kind of value. It's not entirely true. There is some things I'm sweeping under the carpet, but that's the gist of it. So we are plotting in terms of s. You can see our height is a measure of like how likely it is that it's going to happen. Nice. So we have got a very important result, the Euler-Lagrange equation. Why am I? And I guess if you don't have to understand where this equation is coming from. As you can see, it required some intuition. Doesn't matter. The main important thing is we have this equation now. I should also mention I have switched very deviously my integration symbol, my differentiation symbol, where this is basically what I mean with this is we are taking the derivative of our Lagrangian, which is a function of more than one variable, but we keep v fixed. So we pretend that v is a constant, and we take then the integration of x. So for example, if we have a function x comma y equals xy plus x squared, something, then the partial integration, as it's called, this is just pretending y is just constant. So we just pretend it's a number. So taking from the first term, we get this. From the second term, we get this. Similarly, if we take the partial derivative to y, we pretend that x is a constant. So the second term vanishes. We just get x. That's a quick crash course on partial derivative. So that explains my change in symbol. I'm going to erase this. So we got the Euler-Lagrange equations. Let's see what we can do with them. We have seen two examples already. In the Newtonian case, the first one is the free particle. So let's just go back to our free particle. Now, we know the Lagrangian is the sum of is the kinetic energy minus potential energy. So who paid attention and can tell me the kinetic energy of the free particle?
I was about to ask that, just out of curiosity. What is the kinetic and potential energy of a free particle? Just to fully check.
There we go.
E squared by 2m. Oh, the professional way as well.
I'm going to write it as a half mv squared.
Yeah.
Don't worry. Yeah,
Zero.
exactly. Minus 0. So let's actually check this equation now. We can do this now. We have the Lagrangian now. It was very easy to find it. We just needed a kinetic term and a potential, 0. You can argue we knew this already. Yes, but that's because we're fact checking right now. So, yes, that's what I'm saying. The kinetic energy comes from the Newtonian formalism. But the funny thing about kinetic energy is that it's kind of the same for every system. Kinetic energy doesn't change. So, no, yeah, we're not using Einstein here. This is not relativistic. We're still classical.
Not yet.
But don't worry, we also will get there, just not today, unfortunately. So let's just use this Lagrangian. Let's first of all partially differentiate. Partially differentiate. Yeah, with respect to x, we see that this means setting all the v to a constant. Which means this is just 0. Now the other one, with respect to v, this is going to give us mv. This factor 2 is going to negate this factor, so we're just getting mv from there. So what the Euler-Lagrange equation are telling us is that, see them again, minus the time derivative of the second part equals 0. Now, what do we know about the derivative of velocity with respect to time? That appears to be the acceleration. So what we get is mass times acceleration equals 0. And now, let's compare these. What we saw in the free particle, could we get the stream to the free particle in the classical case, perhaps?
It was at the free particle.
Thank you to my favorite mechanic. So what we saw is exactly the same equation. So until now, our formalism works out perfectly. That is lovely. So once again, we get that the force equals 0, even though we didn't even use the notion of a force equal to 0. And we can solve this equation and just find the same linear dependence of position once again on time. So now let's make it a bit harder and go for the...
In other words, as you're noting down, basically we just figured out a thing about a free particle that we assumed on the very beginning. But now, just from the fact that we knew the energy of a free particle, we were able to figure it out without the notion of force. Or in other words, it's coherent.
Who remembers the energy, kinetic or potential from the harmonic oscillator? And don't tell me you guys didn't notice this question was coming.
The board was all divided into two and such.
That's the force, Cordy. I mean, for the kinetic energy, as I just said, it's going to be the same thing again. And for the potential energy, exactly, it's going to be a half kx squared. We can fact check this with the previous one. So we are going to use the Euler-Lagrange equations again. I'm going to highlight them because that's how important they are. So let's just go right back to it. Derivative with respect to x is giving us, in this case, not 0, but we get minus kx. The 2 is going to cancel the half. And the derivative with respect to v equals, once again, just mv, which means that the time derivative of this is going to be ma again. So that changes. So what you can already see is that from the kinetic energy, we get most of the time the mass times acceleration, so Newton's law. And the potential energy sort of determines the force. In this case, exactly determines the force. So let's combine them. We got minus kx from our derivative with respect to x. We then get a minus, and then we get ma. And this needs to equal 0. So if we rewrite this, we get exactly ma equals minus kx. And this is exactly the force that we found before, once again. So at least for these two examples, our formalism is nice. It works. That is good, because that means we can, well, generalize it. Do we have some animations, by the way? Because I forgot if we do have any left.
I mean, not really. We can change the landscape for the path integral.
We promised that.
We can in fact do that. Do you have any? Do you want to? Do you have any functions in mind? I should pop in there real quick.
Anything... Let's just say I am feeling massy today.
You're feeling
a
massy.
Particular mass.
A certain particle of sorts that you would like perchance to see.
I believe in the folklore it's called the gold particle. Perhaps we can show the potential of that one.
So some like a hat is what you want, like a very specific kind of hat.
Yeah, I was thinking Mexican.
Well, in that case, say no more. And where should I place this point then, Remko? Would it be would at the center be fine?
Perhaps let's just do it in the center.
Let's do it.
And perhaps let me do some improv right now. This is not prepared, so there might be mistakes in this, but this is the famous Higgs potential. It's this little Mexican hat form. It determines the mass. And in its current state, it is at a maximum, which means it's a stable point of the action, which means on its own, it's not going to move. Now, this is how we predicted, or at least how we proposed that the universe started, with the little system, our universe, exactly in the middle of this potential. What this means is that nothing had mass, because mass gets created down in the bottom of the hill. So now we are in the universe that is exactly massless. Every mass doesn't even exist. And look at it. Look at our universe up there. It's so adorable.
Yeah, it's just fine, completely relaxed. Uh, there's a rest point, by the way. There is the place where it's sitting. It doesn't actually have a gradient going anywhere in any direction. If this point in this abstract space moves in any direction, it would be on a pretty steep gradient. But right in the dead center in the middle, it's not. So
On
anything we
that
should
sound,
anything we should do with
I
this Remco, or just actually no, you keep going first.
yeah, no, Pandasan asked a question, or at least mentioned that just pretending neutrinos didn't exist. It's actually way more fundamental what I'm saying, what we're saying. But the neutrinos didn't have mass. They actually didn't have the notion of mass. Because the Higgs particle did not, well, exist in the way it does today. So there was nothing to give it mass. Now, let's turn on some quantum fluctuations, shall we?
Oh, so all of a sudden it was just standing there peacefully, and then all of a sudden, whoops!
Oh no, we added some energy.
Oh
Oh
no!
no, it's going. We've
It
fallen.
went, it rolled down, and it found a place to rest.
If you want some cool physics words, you don't have to understand this. What just happened is a symmetry breaking of some kind, and associated with a symmetry breaking are so-called Goldstone bosons. They are created when every symmetry is broken. They usually are quasi-particles. In this case, it's the Higgs mechanism. They are actual bosons. So these are the Higgs bosons that just got basically released into our universe. And this is what gives us all mass.
Yeah, we
It's
did just go
so
from
simple.
we did just go from classical mechanics to creation of the universe in the space of 3-ish minutes.
Yeah, this was also not planned. So, so this is a bonus for the people that stayed.
Yeah, I mean, not planned. Okay, well, to be fair, it wasn't planned. We were just having fun and testing it out on the Higgs, because what else to test it out on? But this is a neat example, actually, of because really often when you learn about physics, you don't often get it tied to something this advanced this simply. It's not often that you can graph something as advanced as Higgs.
I think it's very beautiful. This entire symmetry breaking of this kind. Wow.
Yes, it's truly lovely.
All right, shall we go back to classical stuff?
Oh yeah, sure.
Let's do a fun section, even though this was already a fun section.
Everything in this lesson was a fun section.
Yes. So, let's just showcase how important or how useful this formalism is compared to Newton's formalism. So in Newton, when you wanted to describe a system, you would have to give a specific force. You can obviously guess some forces, but most are just doesn't make sense. Whereas with the Lagrangian system, what we can do is we can make our own Lagrangian. So what we know is, well, we know we have kinetic energy minus potential energy. Probably, I don't think I said this before. I should maybe add this as a disclaimer. Not all systems, especially when you go quantum mechanics, have this form. You can't describe every system separately in kinetic and potential energy. But in classical systems, we should be fine. And also, I think when there is actual time dependence, this is going to get messy. But once again, we also don't look at that. So we have a Lagrangian. We know it's kinetic energy. Its potential energy is up to us to fill in. So does anyone have like a fun suggestion we should try?
Any function will, well, almost any function will do.
And the only condition I'm asking here is don't let it depend on v, because if you let it depend on v, then it's not longer. Things are going to get weird. So I want a function of x only. Yeah, no, Cordy, I know what you were doing, and then that's called sabotaging.
2x squared. Oh, that is brilliant, actually.
Yes. So let's do 2x squared first. Let's go back to the harmonic oscillator. Because you have just described the harmonic oscillator for k equals 4. So I can tell you that the what you get is a linear action. Let's just highlight it once more. This is the term you're describing. And the minus sign is by virtue of the minus sign in the Lagrangian. So yes. So we can do the Euler-Lagrange equations, we can solve them again. We get the same Newton's law, except now we have a force of minus kx, so it's linear in x. In this case, it should be minus 4x in your specific example. So another example. I see exponential energy. All right, I can. Any other suggestions?
E to the x.
There is, of course, we could try p is e to the x. Is there any other suggestions? Something, something that might be interesting, for example, like a power of x?
How about x to the third?
I was hoping Chat would say that.
I don't mean to break the character too much, but before the stream, Remko asked me for 2 suggestions, and pi squared, that doesn't have x in it.
Yeah, I would like an x there. But I mean, x to the pi.
To the pi. Oh, goodness
Man.
gracious me.
Okay, you know what? You guys are. I will make it myself difficult. Instead of doing an explicit function, I am going to say we are having kinetic energy like this.
Oh,
Just some potential energy. You can fill in your e to the x here. You can fill in your e to the ix here. That's a phase. Why would you even put a phase in the potential energy? You can fill your x to the pi in here. It's all left to interpretation. And this is why this formalism is so powerful. I can make it as global as I want. So let's just solve it. We know this one. We can simply just write it. It's minus the derivative of this. Now I can't go further because I don't know what this means. But in case of the e to the x, we would have e to the x again. All right, let's do the other one. This is once again mv, which means that if I am already, I'm doing it a bit faster because we have seen this a couple times. This is already a. This means that the Euler-Lagrange equations give us, well, we should take care of the minus sign, so we get minus this one and minus ma equals 0. Exactly. That's why I did it this way. What we get is ma equals minus Vx. And this is potential energy. Or well, rather the V is potential energy. So we're taking the potential energy with the derivative with respect to x. And if you just go back to our harmonic oscillator, specifically the energy part of the harmonic oscillator, then the classical one.
Classical, right?
Please. Here, yeah. Then look at that. This is how we defined potential energy in the first place. So what we did is starting with potential energy, and we just defined force as Honda-san was mentioning. And this is deviously why it didn't matter which functions you were going to say, because I was going to generalize it anyways. I'm sorry. All right. So what you can do with this formalism is any function of x can just be plopped down. You will get a force equal to the minus the derivative with respect to x. Also, And I am not going to do this. But what you could do is, indeed, as was mentioned in the chat, you could think of potential energy in the form x squared v, for example, to the fourth. So you could couple, well, velocity and position in physical terms. And you just need to do some integrations. Well, no, differentiations, and you will find your equation of motions, but usually they are difficult to solve or impossible to solve. In that, like, if you want to find x of t equals something, it will not be analytically possible. So that is the strength of this entire formalism. You can just write down whatever you want. You don't even know if it has to mean something. You write it down, you solve the equations, you see the behavior of the equation of motions, and, well, you just see if it could make sense physically. This is how we do it in quantum field theory, which we will come to eventually. This is how we do it in general relativity, also something we will cover in future live streams.
Yes, but so far, one last time, let's ask the question of, is everything clear? Because, just to give you all some perspective, this is what we've covered today. It is a lot. It was, in fact, quite a fair bit lot. So, if anyone has some more questions, I suppose right now there's one thing, because it's clearly created a lot of confusion, which we can go over again, would be the action, which, to be honest, we knew would cause confusion, didn't we? Don't forget the phase space. Oh, everything is reflecting light.
Did you mean invisible? I mean, the action is a number, in this case, not a vector. So the action, like, it doesn't make sense to talk about an equal and opposite reaction.
Because in this case, the action is different from the action, the Newtonian action.
I mean, as a physicist, I do not agree with that terminology.
No, because...
But I guess what you mean.
You know, does the action have an equal opposite reaction? Doesn't really make sense for this action.
Oh, you know what? That makes sense. I see your point now.
Yeah. Different... This question was funnier in my head, sorry. Oh, no, don't worry, we got it. Well, question of phase space, which I completely missed. Do we redo the segment or do we leave it for the video? Because it clearly is unclear. So, this is the question. Do we redo it on stream right now? Or do we leave it for the video post-stream? Remko, that is the question to you.
Yeah, I know. I'm thinking on it. It's a good question. I'm thinking, because I don't think I can explain this in much of another way.
Yeah, I feel like this would just require some more dedicated visualizations, maybe.
I can make it up to you guys, and I'm doing this on behalf of Make It, so I hope he agrees with me. We will do a slightly extensive part in the video on the action, where we explain it more concise, more clear,
Yeah.
from a more theoretical foundation.
Hopefully more obvious.
Yes, and if there's then any questions, we can just cover it in the conventional live stream. Because right now it's a very confusing and abstract notion. It's just slightly difficult to explain on point. It makes no sense. I get it. I have struggled for a long time with the action as well.
Yeah, before the stream we knew this was going to be a problem.
So it's going to be in a video. We're going to cover it, and you guys will understand. And if you don't, you can ask questions. Instead, for now, I think it's really. Let me give like a short, like let's just say a short cliffhanger for next time. So, if we have this Lagrangian formalism, kinetic energy minus potential energy, or actually, let's just consider the Hamiltonian formalism in this case, which means the plus. What we then could do, let's just first write it in terms of. Actually, let me write it in terms of momentum in this case. And we also have some. We also have some potential energy. We are talking about Hamiltonian, that's why there's a plus sign. What we could do, and this is perhaps a really important step to take, is if we have this Hamiltonian, and we just by some sign of divine intervention